Thermochemistry. Thermochemistry, this is going to be a fairly quick unit, fairly straightforward. When you go on to take AP Chem, we do thermodynamics and thermochemistry together. It's a little more involved, but it's still, even for AP Chem, it's one of our easier units. Okay. First of all, we need to talk about the law of conservation of energy, because we're going to be talking about heat energy. The law of conservation of energy states that energy can either be created or destroyed, but can be converted from one form to another. Anything that's a blank in your notes is going to be probably in red. There's one slide that it's going to be in blue, and you'll see why. But the law of conservation of energy is also known as the first law of thermodynamics. So we can convert it, but we can't destroy it or create it. Unfortunately, oftentimes when we are converting that energy, we are converting it into an unusable form. In the case of combusting fossil fuels, we're not losing that energy, but we're just converting it into a form that can't be used as energy for our purposes. Heat is something we're going to be talking a lot about in this unit, and heat is represented by the symbol of a small q. I don't know why they used a small q to represent heat, but it is the process of energy flowing from a warmer to a cooler object. That is very important to remember. Warmer to cooler. Okay, always flows warmer to cooler. Obviously, when a warmer object loses heat, its temperature decreases. And obviously, when a cooler object absorbs heat, its temperature rises. That makes sense, right? Okay. There are 3 types of heat transfer that you will be responsible for knowing. I would definitely know these for a test. This unit has quite a few definitions in it. Types of energy that we want to talk about are conduction, which is 2 substances in direct contact. That is going to be, for example, a pan on a stove. They have to be in direct contact with each other. So we put a pan on the stove, we turn the stove on, regardless of whether of it being gas or electric. If it's in direct contact with the metal heats up, okay, and gets hot. Convection is the transfer using density-driven flows. It is for fluids. That means liquids and solids. Not liquids and solids, liquids and gases. Those are going to be density-driven. For an example of that is boiling water. So if I put water in the pan that I put on the stove, the pan heats up because of conduction, but the water starts to boil because of convection currents. So what happens is, as water gets warmer, it gets less dense, so it moves to the top. And the water at the top, that is more dense because it's not as hot, goes to the bottom, and then it's constantly moving around. If you've ever seen or have a lava lamp, how many of you have ever seen a lava lamp in your life? That should be all of you. How many of you have a lava lamp? Yeah. I used to have one in my classroom and it broke, and it's a perfect example of density-driven convection, because what happens is you have the light bulb and it heats up the wax that's in there, and as that wax gets warmer, it gets less dense, so it goes to the top. And then at the top, there's not a light source or a heat source, so it cools down a little bit, and so it gets more dense, so it goes back to the bottom. So it's just constantly going round and round and round, up and down because of the density, the change in density. It's very slight, because obviously when it gets to the top, it's still warm enough that it's not solidifying, okay? But that's how convection works. And of course, radiation is infrared energy, things like the sun, or things like tanning beds, which are horrible for you. They're worse for you than the sun. Please do not use tanning beds. They're very bad for you. Here's just some images of conduction. We're going to put an X over this because tanning beds are bad for you. Don't use them. Put the big X in circle. Because it's more intense radiation than your sunlight. And so that's why you can tan in 10 minutes instead of whatever it takes you outside, because it's more intense. So it's actually worse for you. People think it's healthier. It's not. Okay? Just going to tell you that. Measuring heat. The amount of heat required to raise the temperature of 1 gram of pure water by 1 degree is called a calorie. The kind of calories we talk about in our food is actually a kilocalorie. We just say calories, but it's That's a food calorie, is a little bit different. Okay? The SI unit for heat and energy is called the joule, Joule, and it is designated with the capital J. And 1 joule is the equivalent of basically 0.24 calories, or 1 calorie equals 4.184 joules. Temperature is the measure of the average kinetic energy of particles in matter. And I want to show you this. Kinetic energy, the formula is actually 1/2 mass times velocity squared. So the temperature is not actually in the formula, but it is a direct relationship between temperature and kinetic energy. Because what happens to particles as I heat them up? They move faster, and so because they move faster, that shows up in the velocity. So it is a direct relationship between temperature and kinetic energy. Higher temperature means higher kinetic energy. Lower temperature means lower kinetic energy. We measure temperature, of course, in degrees Celsius or Kelvin. We do not use the Fahrenheit word in here. And then this is an important concept, so I wrote it really big. So you should star it, circle it, put a smiley face by it, draw lots of arrows to it. But temperature and heat are not the same thing. Temperature and heat are not the same thing. I'm going to say it one more time so you know that it's important. Temperature and heat are not the same thing. Specific heat is the amount of energy that is required to raise the temperature of 1 gram of pure water by 1 degree Celsius. Okay? Specific heat capacity, sorry. And it is different for each substance. For water, the specific heat of water is 4.18 joules per gram times degrees Celsius. Okay? Water has a relatively high specific heat compared to other things. And I'm going to show you a table in a second, and you'll see what I'm talking about. Each substance, because they have different compositions, have different specific heat values. So if you notice water, it's a lot higher than metals. Okay? Something that is a good conductor is going to have a very low specific heat. It means it doesn't take it very long to heat up, and it cools down very quickly. Okay? So if I put a metal pan in the oven, make some cookies, the pan gets hot really, really fast, right? And then when I take it out and I set it on the counter and I let it cool while the other batch of cookies is cooking, by the time I'm ready to put it on there, it's already cooled down, right? It's not very hot anymore. What about a pot of water? If I boil a pot of water, does it take that water, does it heat up very quickly? No. Let's say I boil the water and I turn it off. It stays warm for a really long time because it has a high specific heat. So it takes it a long time to heat up, but it also takes it a long time to cool down. So things that make good insulators have high specific heats because it takes them a while to heat up and cool down. It's good that water has a high specific heat because our waterways don't freeze as easily as they would if it had a low specific heat. Okay, that's why even after it's been hot outside, let's say it's been 10 days of 80-degree weather, and you go jump in your pool and you're like, oh, it's so hot outside, I want to go jump in the pool, and the pool's still pretty cold. It's because of the specific heat of water is very high. It takes a long time for it to heat up, but it also takes it a long time to cool down. Okay. Like the beach, well, I mean, obviously the beach is going to take even longer because it's a lot larger quantity of water. Okay? It has to do with the mass too, which is what we're going to see in a second when we see our formula. So the heat absorbed or released by a substance during the change depends on not only the temperature, but the mass. Okay? We're going to use something called a calorimeter to measure the temperature change. And basically a calorimeter is something that minimizes the surroundings effect on the system. So it basically it maintains the temperature of what's inside of it. How many of you have a Yeti cup? Your Yeti cup is a calorimeter, an insulated cup, but it's also a calorimeter. So it's minimizing Either if you're drinking something hot, it minimizes how much heat can be lost to the surroundings. If you're drinking something cold, it's minimizing how much heat from the surroundings goes into your system. So it keeps your iced tea cold longer. Okay, but basically it's a calorimeter. Calculating with specific heat, here is our formula. We call this the MCAT formula. One tiny mistake is this is supposed to be a capital T. So I'm making that a capital T now, because we designate temperature with big T, not little t. And then here's what all these things stand for. The formula's on the next page. Oop, too far. Uh-oh, the gremlins, there we go. Okay, so MCAT, mass is M, C is your specific heat of the substance, and T is your delta T. This is going to be an important part of delta T. Delta means change in, but we're always going to do final minus initial. So take your final temperature minus your initial temperature. So if I give you a formula, you know what that means. We're going to do some calculations. You can probably just use your calculator on your phone. Nothing fancy here. Okay. It says how much heat is given off when an iron bar cools from 940 to 50 degrees Celsius. So first of all, we're going to need to use this formula. Q is equal to MC delta T. Gave us our mass is 869 grams. I will be giving you the specific heat value unless I'm asking you to solve for it. I'm not asking you to solve for it here, so I'm going to tell you that it's 0.45 joules grams degrees C, and that is for iron specifically. And then delta T, final minus initial, is 50 minus 940 equals 890 degrees Celsius. Is that right? Yes. So now it's plug and chug. 869 grams, 0.45 joules grams degrees C, and then negative 890 degrees C. So Q is going to be equal to a negative, we need 3 significant figures, 333. All of these have 3. I think it's 348,000.
Yes.
Is that what y'all got? And that is joules is my answer. So that's how much heat that iron bar is losing when it cools down. Okay? That's how much it's losing. So there's a lot of joules. It's actually not there. Seems like a lot, but it's not. Okay? Is everybody okay with that? That's basically the equation you're going to be using on your worksheet today. Sometimes it will be asking you to solve for change in temperature, sometimes mass, sometimes it'll ask you what the specific heat is. In your worksheet, in the beginning of them, I give you specific heats. Later on in the worksheet, if I already gave you the specific heat of aluminum, it does not get repeated. You have to go back and look at it, what is for aluminum. I underlined that at the top so you'd see that. Okay. Already did that one. Calorimetry is the study of measuring heat changes from chemical reactions or from physical changes. Which is, you see back on the lab tables, you see those little silver cylinder looking things. Those are your calorimeters. Okay. There's all kinds of calorimeters. The simplest kind is a coffee cup calorimeter, which is basically taking 2 coffee cups and putting them together, and now you have a coffee cup calorimeter. Woo, fancy. Okay. There's things called bomb calorimeters. I don't know why they're called bomb calorimeters, except that if they were to, they're like sealed containers that are pressurized, and so technically they could blow up if the pressure got too high. I used to use them when I worked at the plant, but that's usually how we do for gases and stuff. And it minimizes the surroundings interference. Okay, so here we have an example. This example is going to be exactly like how we're going to do it for the lab tomorrow, so pay attention. We have a sample of copper. It's being heated and then placed in a calorimeter containing some water at a different temperature. The final temperature of the metal and the water together is 21.8. What is the specific heat of copper? Okay, so we already know what the specific heat of water is. What is it? 4.18. Okay. Joules, grams, degrees C. So what I need you to understand is that whatever heat that water is gaining, because it's clearly gaining heat, it's going from 19 to 21, okay, whatever heat that water gains, because of the law of conservation of mass, it's going to be equal to the amount of heat that copper loses. But it's going to be negative because it's losing it, okay? And that's due to the law of conservation of energy. Energy cannot be created or destroyed. It can only be converted. So however much heat that water gains, that means copper had to lose that much heat. Are you okay with that concept? Okay. So we can calculate how much heat water is gaining because we have specific heat, we have delta T, and we have the mass. So let's go ahead, because we're going to need both of them. We're going to do the delta T for water and the delta T for copper. 21.8 is the final for both of them. That's what they ended up with once I mixed them together. So 21.8 minus 19.6 gives me 2.2 for water. 21.8 minus 95.4 is going to give me a negative 73.6. Okay? So now we can get how much water gained. So my water was 75 grams. 4.18 joules, grams, degrees C, and then 2.2. So I get that my Q for water means it was gaining 690 joules of heat. That's how much it gained. So that means that I'm going to do this in a different color now, that Q of copper is a negative 690 joules. Because that's how much it lost. So it lost that much heat because that's how much water gained. So now I can take this equation of Q is equal to MC delta T, and I can solve for C, because that's what it's wanting. So I would say C is equal to Q over M delta T. So negative 690 joules. Mass was 46.2 grams, and then negative 78.6 degrees Celsius. Not 78, 73, sorry. So when I do all that math, my negatives cancel each other. Here's a clue. If you ever get a negative value for specific heat, you did it wrong. You can't have a negative value for specific heat. It comes out to 0.200 joules, gram, degrees C. So that's how you solve for specific heat, which is what you're going to be doing in the lab tomorrow. You're going to all have different metals. You're going to heat the metals up by putting it in boiling water, and then you're going to take that metal out and put it in the calorimeter where there's already water, and you're going to figure out, based on the temperature change, based on knowing the specific heat of water, what your specific heat of your metal is. Okay? So that's exactly what you're going to do tomorrow. Okay? Any questions on this? This is the most important concept of that right there, that whatever heat is lost is gained by the other thing. So it's going to be the same magnitude, just different sign in front of it, either positive or negative. Okay, that brings us to endothermic and exothermic reactions. Okay, Endothermic reactions absorb energy from their surroundings. So that means Q is going to be equal to a positive sign. So anytime Q is positive, it is an endothermic reaction because I'm adding energy or heat. Okay? Exothermic is releasing it, so it's losing it, so Q is negative. So just like in that last problem, we said the water was gaining heat, so it was positive, Q was positive. The metal was losing heat, so the Q was negative. So in this case, heat, Q is positive because heat is entering into the system. The system is absorbing it. That's why it feels colder. In exothermic, it is releasing it or subtracting it from it. So heat is leaving the system and going into the surroundings. Basically, the system's what you're studying. The surroundings is everything else. Sometimes it's referred to as its universe. Okay. And then last thing for today is these graphs. These are called energy diagrams, and you do need to recognize these for a test. When you have an endothermic reaction, the products have more energy because they absorbed. So they're going to have more energy than the reactants. So we started out down here. We absorb some energy. We end up here. So what do you think it looks like for exothermic? Flip it. Okay? For exothermic reactions, we have released energy. So our products are going to have less energy than our reactants. And that, my friends, is where we end today.